convection. So you want to run over? Yeah, I will do that. Yeah. So convection, right? Ready? When heat is applied to the bottom of the beaker, the water at the bottom becomes warm and it expands, making it less dense. And what has happened to something that's less dense? It will rise, right? So as a result, it rises to the top, and the cooler water from above takes its place, and the process is repeated. The circulation of water in this manner is referred to as convectional currents. The process is called convection, and it can occur in both liquids and gases. Convection is defined as the process in which heat is transferred through a fluid by the movement of the fluid itself. This can be observed in ocean currents and winds. Most fluids expand upon heating, except for water between 0 and 4, which contract. Right? Just a quick diagram on how this works. You all may or may not remember this, but right? If you have a container, right, and the container is filled with water, and you apply heat here, what has happened is that the hot liquid will rise, and the cool will take its place. And what you have being produced is convectional currents. All right. So if you look at water closely while you're heating it, you will see the currents. If you look closely, you will see here where it's warm up. You will see some fluid rising, and then the ones here taking its place. Right. So next time you're heating something in a clear container, look at it. Right. And what you have being produced here is convectional currents. All right, which we could see, for example, in you all remember in geography, you would have seen in land and sea cruises. So, like during the day, which one is hotter faster? The land or the water? Land. So the land will heat up faster, right? So you have water here, the land will heat up faster, and the air above the land will rise, and the cooler air from above the water will take its place. Right? And then in night, what has happened? The reverse, right? The reverse, right? So the warm air above the water will rise, and the cooler air from the land will take its place. That's okay? Those are examples of convectional currents. Now, what we need to focus on is thermal radiation, right? There's no formula for convection at this level, all right? So we have to focus on thermal radiation. So thermal radiation can be defined solely as in terms of the body's temperature as being the EM radiation it emits. So radiation is really the emission of electromagnetic rays called what? Anybody remember the main type of EM waves? What's the main type of EM waves that a hot body will give off? Like sun. Sun gives us what? Right? UV and infrared. Right? At temperatures below about 1000 degrees Celsius, the energy is associated entirely with infrared. At higher temperatures, visible and ultraviolet radiation. When thermal radiation is incident on the body, some of the radiation may be reflected and some transmitted, and some may be absorbed and produce a heating effect. So the law that we have to learn is called Stephan's law. Right? So let's make a note of it. Stephan's law. Stephan's law is used to determine the amount of energy emitted by a black body. It states that the total energy radiated per unit time was energy what's energy radiated per unit time? What's energy per unit time? Power, right? The power. It states that power per surface area of a black body is proportional to the fourth power of temperature. So basically it's saying this. Right? It's saying that power is equal to Stefan constant by the area by temperature to the power of 4. Right? So make a note of the one in red. Huh? Scroll up a little bit. To write all that in different handout. Just write Stefan's law, power is equal to Stefan constant by area by temperature to the power of 4. Okay. Right, so but really and truly, right, for the power to really flow from the black body to outside, there must be a temperature difference. Okay, there must be a temperature difference. So the one that you will really be using is this. Oh, by the way, write down the value for Stefan constant. Write down the value here for Stefan constant. Write down the value for Stefan constant. Right? Just write this 5.6. You're wrong, we go 5.7. Right, so that's Stefan constant, and the relationship that we are actually going to use is this one here. Right? So if a black body whose temperature T is in an enclosure at temperature T naught, the rate at which the surface area A of the black body is receiving radiation is given by this. And the net rate of heat loss is given by this formula here. So write this down. Don't use energy here, use power, right? Some of you all might think that energy is like power. That E is energy per unit time. Power is equal to that. Stefan constant, some like sigma. Standard deviation. Joseph, you recognize that? Size. All right. So nice. So how do we know if a body is given off? If a body is radiated, it must be a hot body below 1000 degrees Celsius, right? And of course, there must be this temperature change, right? That's okay. How do we know when to use the conduction formula? When there's a solid and there's a temperature gradient. All right. All right. So let's take a look at how to apply this, right? Are you okay with that? Right. So that's the end of heat transfer theory-wise, right? Next is kinetic theory, but we're not going to rush that. We'll just do that next. Hold on, just on it. Not this one. Try this now. Oh, temperature must be in Kelvin, right? Try this here. Temperature must be in Kelvin. It's sick. Wait, fast. There you go. Up. Huh? Just take it forward. What I can tell it forward. Tapi 自己来先作业，这一点出生就他们来路上要并我们我的身体来信息，老王他帮，要不然我这我跟你说，要对。哦，不会也是，又来买东西啊，来算是这种，就是。I go, I go, I go. I think in the one, I think in the one. So I know about this we have. That's that. I like number that. It's 6 7. I can't do that for the number. If I can't, I think it's something about. Yeah, clearly you treat you. Yeah, something else. Here, huh? At least we are nothing but So what they asked for? They asked for the rate of heat loss, so they want power. So that's Stefan constant by the area by T1 to the fourth minus T2 to the fourth. Huh? Yeah, Stefan's constant what I gave it before, 5.6 plus 7. 5.67 by 10 to the minus 8, right? Why was that? I remember I gave it minus what? Minus 8 here. Minus 8. The area is 2. The area is 2, right? And which one was the larger temperature gradient from the skin? So it's 36 plus 273.15. Okay? You have to use 270.15, huh? How much is that? 309.15 to the power of 4. What's the next one? 24 plus 273, right? So that's 297.15. That's what we're using now. 15, yeah. Right? Using 0.15 from now on, right?
So I use this.
Hmm? Well, I use them for. I mean, that's 0.5. I think that's not just like using 10, but gravity has 10. Now you're using 9.8. Work it out. Tell me what you got for your power. Let's see. Remember, you're always radiating from the higher temperature to the lower temperature, right? Yeah. 151. So come another half. 151.7. Yeah. Anytime now. What just happened? Just jump up. Yes, it can crush it. Right. Everybody get that right? 157? Yeah?
Yeah, 151.
151, okay.
0.7.
0.7. Let's go again. All right, this signal will be how much here. Hold on, let us type one give it some problem.
It's a that's an annual. It was what's up.
But then before it crash, I think I got a picture now. This. There it is. Yes, no, that's something missing. How's the noise give this thing on top of the buddy? Oh, yeah, get? No? Still think I showed you there, but I don't know how to. I don't know what to do now. Alright, anyway, take a picture and then we decided to work it out now. That's the whole thing then. Try that. Right, you'll notice they gave you a little bit of a specific heat capacity here, so you might need that, right? Try this way. Oh, you want a hint now? Right? So you have a furnace. How is the furnace going to let the heat reach from where it is to the beaker with the ice? By radiation, right? So the radiation is absorbed by a Pyrex beaker of 20 grams, containing 50 grams of water and 30 grams of ice in equilibrium. The temperature of the furnace, so they give you the temperature of the furnace and the specific heat capacity at Pyrex. Calculate the time it will take for the beaker and its contents to reach 20 degrees. So what is supplying the heat? Furnace. What receiving the heat? The beaker, right? So you have to create some little equation thing and put them together. I can't really help it too much at all. How to give it the answer. Right? So think about how are you going to find the energy being supplied by the furnace? What do you need? Think of you all said it's radiation, right? So look at the formula of radiation and see what you have. And then see how you can figure out the last part. What is the beaker undergoing? Temperature what? Temperature change, right? So somewhere we're going to have to use E is equal to MC delta theta. Please remember the specific heat capacity of water is 4200, right? Right, they would have given you at the beginning of the paper. And but you have a picture of it, right? Because you're gonna crash this now again, right? No, it's going to specific heat capacity. Time taken for the beaker and its contents to be 20.
67. 42, 72.
Ah,
42.
4200. All right, so you should have all the info. And we know that the one different time, right? We know that there's a temperature change happening. So we know that E is equal to MC delta theta. Somehow or the other, we're using this, right? So think of what's supplying the energy, what receiving the energy. Okay. Right, the ice melting, so they should have given you latent theta fusion as well. I don't have the tools. Sheet 20 of them.
Any fusion, right?
Yeah. So all the info here. Right, so just want to make sure you have an idea what's going on, right? So what's supplying the energy? The furnace, right? So the furnace supplies the energy. What receiving the energy? Beaker, what else? Ice and right. So what receiving the energy? The beaker, the ice, and the water receive the energy. Okay. How you find energy? We know power by time. Right? The beaker undergoes a what? Temperature change, right? MC delta theta. Ice underwent a what? A phase change. Anything else? Temperature change, right? The ice will go from 0 to 20, right? But what about the water? The water underwent a temperature change. So when the furnace supply the heat, it's changing the temperature, the beaker, melting the ice, then changing temperature, and changing temperature of the water. Right? Put in your values, work in kilograms, right? Let's see what you get. Everything right here, right? So what you using to find power? Stefan's constant by area by t to the power of 4, right? And then we need to find T, right? Was the mass of the peaker 0.02 by the 840 temperature changes how much? 20. Mass of the water at the ice is 0.03 by latent heaters. Calculate. All right, yeah. Yeah. Right, sorry. And then M is 0.03, C is 4200, and then the ice will undergo a temperature change at 20, right? And the water will undergo a temperature change at 20 as well. The water was 0.05 by 4200 by 20, right? And you have to make T the subject. Add up all of this and then divide it by Stefan constant by the area. We have a slight problem there. The area is in what? Centimeter squared. So highest convert that to meter squared. Divide by 10 to the power of -4. Right? And then the temperature was what again? Temperature was 1500 plus 273.15 to the power of 4. All over this. Any answers? Oh, go on.
Second, 261, 0.17.
Huh?
261.
Look it up.
Yeah.
What you got?
What's up?
347. Check it back. Check it back again. Again, in the front side. Okay, let's send this pic on the group, right? Because from this flash it up to keep crash. Yeah. How much we got? What you got? 302.5. Christian get our order, so we go with 302.5. 302.5. Just check it back your working and make sure. It's just this divided by this. All right, I'll send the next one in the group. But by the way, you all recognize this, right? This is the conservation of energy. Energy is supplied, converted into these forms. Right? The one in your book there is 2010, I think. Check it and see. There's no diagram, right? So right, we do this properly, we start. Yeah, that work. Right, this question combines everything, right? Last question. Let's try and get it right. 2010. Got to myself. I got to myself. If you want that, one. Yes. Double or either. Huh? Yeah, and it's the conduction in the beginning. Rate of the conduction.
Yes, sir.
Oh, yeah, look.
Okay, one on next one.
So part one is the conduction formula. No, K1 and X1 is only when you have materials of different thermal conductivities. Here's only one material, cast iron. Right? Give them the formula and it's on demand right here. That's demand now. So part one is the formula from last week. Part two is today, and then we'll talk about the part three. Right, I will start doing it just now. Done. You think? Partial, I think about it. Think about part three. Ready? Ready, yeah. Ready, part one. Now, let's show you what's going. Alright, that's now it's done. Is you send any answers? Alright, let's go now. Return reach back. So let's start. What else got part one? So, part two. the calculation, the two answers over there were correct. Right, the two answers I heard were correct, right? So part one, they want the rate of heat flow minus Ka delta theta delta X. Right, so that will be 840 by the area was 4.6. Temperature change was temperature change was 3 degrees. Temperature was 3, right? Because it went from 650 to 647, right? And the thickness was 4 by 10 to the minus 3. How much you all got again? This one. By 10 to the power of 5. Part 2 now. Part 2 is via radiation. So it's Stefan's constant by area by T1 to the 4th minus T2 to the 4th. 5.67 by 10 to the minus 8 by the area. 4.6 again, right? T1 will be the hotter temperature. How much is that? 9, 20.15, right? And what's the final temperature? What's the temperature you're using here? 303. Right. Right? You're using the temperature of the surrounding, which was 30 degrees Celsius, right? What that will give us? 1.85 by 10 to the power of 5 volts. Right? So those are the two calculations. Then they ask us to calculate the heat the stove loses by a combination of conduction and convection in its surrounding air. Explain your answer. Right? So think of what you have, and then I want to hear your answer, right? So this is the heat radiated from the stove, and this is the rate at which it's transferred through. Right? So what they want is to calculate the heat the stove loses by a combination of conduction and convection in surrounding air. Think about it. Okay, when you have a few minutes, just read about the scenario so you understand. Good. You guys understood? And what do you think now? What do you think? What is the heat that the stove loses by a combination of conduction and convection surround? Think that is two, I can't draw it two together, but think you have your little cast iron stove, a little heating going on here, and you have heat coming out from here, right? And it going into the surrounding air that's about 30 degrees Celsius. They want you to find the heat loss by a combination of conduction and convection in surrounding air. So they want the heat loss here. What do you think? Right? If you look at it, it's about, oh, you're not seeing the mark, but it's not as much marks as part one. Probably like one mark. Add them. Okay. So the first one is the heat loss by conduction through the wall. And the next one is from the stove to the surroundings. What do you think again? Emma? What do you think? Look at this value here. This is the heat loss by conduction, right? So as it conducts through the cast iron, this is what it's leaving at. That's okay? And this is via radiation alone. So watch them good. Not minus. Question ones. The question wants the heat loss via conduction and convection. So this value is radiation, right? This value is radiation. This value here is what? Conduction. What will happen when the heat reaches out here? When the rate of heat, remember heat flowing through here, right? One temperature was anyway, one was higher and one was a little bit lower, right? So the heat passing through there. So when the heat comes out here, this represents the heat loss by conduction and convection. Not this. This is pure radiation. This is the value that represents conduction and convection. And I'll say enough. Right? So when the heat is lost, right? This is conduction for sure. Will I agree with that? Right? This heat here, when this heat leaves the body, remember it's going through the atmosphere, right? So the heat that being lost will be via conduction, well, radiation as well, but it will be via conduction of the gas particles and convection of the particles as well. This here is the only heat that we have to consider. If they said heat via conduction, convection, and radiation, then we add that. Right? This is the only value that we have. Remember, we have no formula to really calculate heat loss via convection. Right? So we'll have to take this value as conduction and convection. If they say conduction, convection, and radiation, then we add these two. All right? So this is the only thing that we have to show conduction and radiation and convection. All right, so make a note of that now. Heat loss via conduction and radiation, sorry, convection is 2.77 by 10 to the 5. All right. Please remember, right? Remember conservation of energy, right? The heat loss here is equal to the heat gain here, right? And the heat that they gain in here is this. So therefore, this has to be the energy being supplied for conduction and radiation. I mean, conduction and convection. That's okay? And well, this is radiation. They didn't ask for that, right? All they ask is conduction and convection in the atmosphere on the outside. That's okay? That's all right? All right. So for today,